Hi, it is a lot of work and it seems like it's going to be a fun workshop. Um, I'm planning to give a talk that um, talks about theories where the metric is the dynamical variable. Um, Hopefully in the spirit of the workshop, I'll start off with the effective field theory and try to go to more complete UV theories. I'm going to highlight some of the unusual stuff and so save some of the more usual things for discussion. In particular, there's a lot that I'm going to talk about that I don't understand, but that's a workshop. That's hopefully the fun part of the workshop. So basically, let me start at the beginning. The effective field theory treatment basically has an organizing principle, which is just the uncertainty principle. Which tells you that that things from high energies that you don't know, the unknown stuff is local. The stuff you do know, which comes from low energy, is non-local because it propagates long distances. And that allows you to actually do some calculations. Once you've built this into your theory and gotten used to the way effective field theories work, it basically is a very normal quantum field theory. Basically, you have various fields, you include the metric, you take e to the I action, and you include the various terms that you might do, plus 2 over kappa squared r. But then, since there's unknown physics from high energy that's local, you have to include local terms like r squared. Let's make this be Weyl squared, since that'll be the basis that we do, and continues. And then you put all the matter fields, which also involve G and the various other fields around. Okay. But once you've done that, it becomes just a plain old quantum field theory, and it's not that hard to work with. It's despite the presence of higher derivatives here, it's stable at low energies. And low energies, um, it's a unitary theory. Order by order in the energy expansion. So each time you do more loops, you can do higher powers in the energy expansion, and you get the terms that bring in unitary corrections. Let me just take a second here to say something about unitarity. The thing I want to highlight, and I'll say more about this when we do the discussion section, is Bellman's proof of unitarity is actually very useful for us in that he stays in Minkowski, so it's Lorentzian. There's no Wick rotation used in his proof. It is perturbative, so there's that. There's no restriction on momentum dependence. So he hasn't cut out higher derivative terms when he does that, at least in the proof. And the other feature that's going to be useful is that the only states that are the asymptotic states in the S matrix are stable particles. So resonances can appear as intermediate states, but they don't appear as external states, and they don't appear in cuts. So when you take cuts, you're instructed to take cuts only over the stable particles of the theory. Okay. Let me just give you an example of a calculation. Myself here and try to. The example is going to be massless particles bending around a massive particle. So bending of light. Sorry. By the way, I'll send my script to the organizers and you can see some of the formulas that I'm not going to take the time to write. But how would you calculate this? Well, you basically are calculating a scattering amplitude of massless particle off of a massive one. So you have a big mass M here, and then there's M equals to 0 coming along like that. Actually, let me make a solid line for that too. And there'll be diagrams that look like, for example, this one, where these are now gravitons in the intermediate states. I'm doing one loop now, it's 3 levels trivial. There'll be diagrams that are the same sort of thing like that. There'll be diagrams, there's a lot of them. It's a somewhat painful. Diagrams where the graviton is way up there and another one's down here. Let's talk about that. Okay. And we do this using these modern unitarity-based methods where you're doing it using the cuts. And then you can use double copy relations to simplify all the vertices. So the important feature in the calculation is that these are long distance propagations. So everything here is massless, except for the big mass M there. And so they can propagate long distance. You're looking for non-analytic stuff. Which it means square root of q squared or log q squared. Those are the terms that give you the long distance effects. If they were just powers, you can expand powers in momentum as derivatives of delta functions, and so that becomes local stuff. So all you really need to calculate is the non-analytic stuff. So this immediately tells you that those coefficients that appeared in the Lagrangian aren't going to appear because they're analytic. And so the prediction is going to come out independent of any unknown physics of high energy. It's only dependent on low energy. To convert the scattering amplitude into the bending angle, we use an Eichel method. Let me not focus on that too much. But when you do that, from one graviton exchange, you get the bending angle. B is the impact parameter. From diagrams that look like this, you get classical correction. So it's classical corrections out of a loop diagram. It's 15 over 4 g squared m squared. There's a pi there over b squared. And then there's a quantum piece, which I'm going to start off as 8 c b for bending with some other stuff here. It's g squared 1 power of m h bar and our b cubed. Okay, the feature that I want to say here is that this is not universal in the sense that if I have spin 0, spin 1, spin 2, or gravitons, or spin a half, you get different answers. So this thing here is 371 over 120. For spin 0, it's 113 over 120 for photons, minus 29 over 8 for gravitons. So it's not universal. So we've recovered the classical things from loop diagrams. We've recovered non-universal effects, which it's not too surprising that they're non-universal because there's no real theorems that should say they should be universal. And it depends on the propagation of the individual particles. So this is one where the incoming photon, let's say, propagates a long distance and feels the potential, gravitational potential, not at this point up here, but at this point down here, so a long distance away. That's sort of like tidal effects. Um, so it's what you see is it's not geodesic motion. It's not universal. And so these two features actually are a lesson about at least the effective field theory, is that light cones things like Penrose diagrams, all the classical things that we do in general about general relativity become ill-defined as I approach the boundary of the effective field theory. Here, these are very small corrections, so you can just deal with it as a correction. They become ill-defined. So some of our usual things like our usual notions of causality are likely going to fall apart as the effective field theory falls apart, because we don't even have a good way to define light cones. And so if you're it means that these aren't following geodesics. I can't. Yeah, there's no way I can write out a sort of a modified geodesic that that all massless particles would follow as geodesics at this order, at one loop order. Okay, so clearly the gravity, general relativity by itself, the classical theory, it's geodesic motion. Here it feels so. We normally think of classical general relativity as a geometric theory. It becomes less obviously so. Feels much more like a quantum field theory, where you're sensitive to effects, propagators that feels the effects of distant gravitational fields. So it feels more like a quantum field theory than it does a geometric theory. It's not just radiation action. Here's the diagrams like this, I guess. These are ones where it's the photon itself that's propagating far away. Whether I can come up with some definition of radiation reaction that holds it this way, I don't know, but it's a field theory. Okay, and so yeah, so certainly that would be one of the issues if you want your operators to commute outside of the light cone and you don't have a well-defined light cone, something gives. It's also you don't know which of these particles to use as your timing particle. If you're saying, does the signal arrive too early, too late? Which do you use, the graviton or the photon? They're following different trajectories, they'll arrive at different times. Okay. It's just sort of an indication that things are falling apart like that. Yes, okay.
So the dependency of the changes to the spin or the helicity, right?
Well, it's not so much the helicity itself. I mean, we could do helicity dependent corrections. These are independent of helicity. We've summed over helicities in doing this. It's really the types of interactions that each particle has. Each particle has slightly different interactions. They're not.
You cannot really say for spin one you get something, for spin one out you get something.
Well, we're using a particular Lagrangian. For the photon, we get something. For the spin zero, we get another thing. Well, no. So effective. I'm going to talk. This is effective field theory. Okay. Now I'm going to break it down. Okay. Now I'm moving outside of it. So there's two issues. In the UV. And it's good to think of these things as two independent issues. So the effective field theory is going to break down in the UV. Everyone. would agree with that one. One of the issues is the infinite number of parameters. Okay. If I do matter loops, so when I do a matter loop, matter loops produce corrections of order curvature squared at all orders. So you do 3, 4, 5, 6 loops of matter fields, you always, it's R squared. So you need those terms in your action, at least in the effective field theory, to absorb the divergences that you get here. If I do gravity loops, gravitons, when I do one loop, I get R squared. When I do 2 loops, I get R cubed. When I do 3 loops, I get R to the 4th, etc. So there needs to be coefficients. Will be effects at all those orders if I do enough loops. So one of the problems, of course, then is this has an infinite number of terms in the effective Lagrangian, and they all have different coefficients. At some level, some of these simple predictions, this was independent of the coefficients, but at some level, you're going to run into them through at higher loop orders. But there's also a second one, is that the amplitudes all get large at large energy. High energy. So the matrix elements in particular tend to be, something like G energy squared at tree level. Then they get corrections 1 plus G energy squared with both local terms and non-analytic terms. And then there's E squared E to the 4th plus etc. So all these terms that we don't know in the Lagrangian, they produce effects in this energy expansion that blow up at the Planck scale. And they blow up the more unknown they are at low energies, the more they blow up at high energy. So the E to the 20th is more blows up faster than the E to the 2. So we have this feature that all amplitudes blow up. These are independent. They would happen even if these coefficients were known. So let's imagine I came up with a theory that predicted these coefficients, the amplitudes would still blow up. Okay. So various resolutions. So in effective field theories, we have examples where you get only new degrees of freedom. So it's just new. Example here is like chiral perturbation, the theory of pions at low energies is resolved by becoming QCD at high energies, and which is quarks and gluons. There's no more pions in the high energy theory. This is sort of the default assumption that something's going to happen with this, and the metric and all these variables that we're playing with are not going to be there anymore. But you could have the same degrees of freedom, well, with some maybe one new particle or new interaction, new ingredient, some new interaction. And again, chiral perturbation theory could have been resolved by the linear sigma model. We did that. There is, however, the Witten-Weinberg theorem, which tells us roughly that there are no ways to make composite gravitons. It's more technical than that, but roughly. And so you're not going to do something like chiral perturbation theory where you make the gravitons out of QCD. The Witten-Weinberg theorem forbids that. So either you're going to stick with the metric or you're going to go wildly different. And that's why many of the theories that are UV completions of general relativity are like causal sets or string theory are very, very different. They're not just a simple model building. Okay. All right. That's here. So I'd like to then do an interlude where I talk about the effective field theory to full theory transition. In a way that's similar to what I'll say for the gravity case. I'm going to step away from gravity for a few minutes and try to talk about this transition. So this is a model that Diego, Roberto, and I worked on. And the effective field theory version of it is just a scalar field, d mu phi squared, and then an interaction which we'll call g over m to the fourth d mu phi squared d nu phi squared. So it has a shift symmetry, you shift the field by a constant. And this is the effective field theory version. As an effective field theory, it has the same sort of features that general relativity does. At lowest order, it's the matrix, this thing goes like g over m to the fourth s squared. It's actually s squared plus t squared plus u squared, but I'm just going to call it s squared. So it's just some energy dependent. It grows with energy. As an effective field theory, the loops that renormalize the self energy are zero in dimensional regularization. And if I do loops in the scattering amplitude, this is going to go like g squared over m to the eighth from the coupling constant. Okay, so I've kept m and g as independent variables. M is just there to keep track of dimensions for me. G is the coupling constant. This will go like g to m to the eighth. To get the same dimensions, I have to have s to the fourth here. Okay, and there'll be logs and divergences that come out of that. And so I know that as an effective field theory, I need Lagrangians that look like eighth order, d phi squared box, d phi box squared, d phi squared, eighth order to absorb the divergences. And if I'm doing eighth order, this is fourth order, this is eighth order. I should put sixth order in here between. One box, d phi squared, those respective symmetries. And I can do an effective field theory calculation. And we do that. And you know various things about it. You know that G in the effective field theory is not going to be renormalized because the loops come in at the higher powers. This one will be renormalized, will run. Various things you know. The full theory is going to be the same. But there'll be a 1 over 2 m squared d, no, sorry, box phi plus the g m to the fourth. the same interaction term. Um, this is renormalizable now. It's now one of these higher derivative theories like we all get when we do quadratic gravity. And we can look at the prediction. So we've done the calculation, or particularly Diego did it most fully. And you find various results. This is my EFT, and now I'm adding this term to make it a full theory. It's now a renormalizable theory. Okay. Yes. So in fact, when we do the calculation, we see the correspondence. This theory, when I do one loop, I'll do the scattering amplitude. I'm not going to have time to present it in too much detail, but when I do energies much less than m, where m is the mass of this that sits there. It's the mass of a ghost in this case. I get my effective field theory back. You can just do it. You get the effective field theory. You get predictions for G6. G6 looks like G squared over m to the 8th times m squared. And you get predictions G8 is G squared over m to the 8th, 1 over epsilons plus logs. So it runs. One thing I just wanted to say here is that this, to an effective field theory, is a shocking result. Normally, you think when you integrate out, so this is integrating out this heavy field here. There's an extra heavy field associated with the higher derivative term. When I integrate out the heavy particle, I should expect to get things like go like 1 over m squared. This goes like m squared. So this is not. I'm going to leave that here without any further discussion, but for an effective field theorist, it's funny. Yeah, yes. So little m is in principle a free parameter. If I write the propagator here, this goes like 1 over q squared from the first term minus q to the 4th over m squared. And if I make that so an I there and an I here and an I here, I over q squared minus I over q squared minus m squared. So this extra degree m parameter is basically a heavy massive ghost. Okay. But the other thing I wanted to say, so this is A, B, and basically I get back the amplitude that I expect. I get the energy expansion, I get the 6th derivative terms or the 8th derivative terms, and it's clear I would build up an effective field theory in the usual way there. B, the high energy region, E much bigger than M, has what for me was a surprise. The formula is going to be in the notes, is in the paper, but it basically is that there's the point I want to say is that there's no e to the 6th, there's no e to the 8th, etc. The effects that we're growing here with powers of the energy just totally disappear. So this is also surprising to an effective field theorist. They don't exist. So the high energy growth isn't there. I've been calling this operator melting. Because those operators just disappeared. That's going to be a hint for the gravitational theory also. The other feature here is that G runs. And it was accurately predicted by Diego and Roberto from the functional renormalization group. We'll do more on running in a bit, but that's.
So yeah, in order to shoot some idea, if you're in the I have to shoot.
Yes. Yes.
With the ghost that you're not even treating with any special procedure. So can I trust the outcomes of this?
Well, yeah, I'm just doing perturbation theory. So yeah, I'm telling you what we do if what you get if you do perturbation theory with that one. Okay. Okay. The 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 result of this so now is that the amplitude goes like this, but with a running parameter. So that's it with a running parameter. And there's a few other logs around, but they never get big. They're log S over T and things like that. But we still have this feature, this strong high energy behavior. And that's so basically the matrix elements are still going to go like G of some renormalization scale times S squared. That is not melted away. So you still have that. In some ways, that's a new problem. Okay. So as expected, I'm a bit behind. I want to at this stage shift away from this calculation into a bit of some of the higher derivative aspects. So let me talk about path integrals and higher derivatives. And in fact, this theory sits in this category. Let me consider Z to be d phi just what I had there. 1/2 d phi squared minus 1 over 2m squared box phi squared. Let me just do j phi. Okay. So there's just some general generating functional here. The thing that I want to do is I want to convert this path integral into one now over two fields. And I'm going to do it in the following way. I'm going to introduce an auxiliary field with the Lagrangian A. It's eta box phi minus eta squared over m squared over 2. If I do that, that basically, I take this Lagrangian integrate on eta, I get that interaction right there. And now I've got an auxiliary field, and then I do a shift. Phi is equal to A minus eta. It's a new field. This is then by transformation. This turns this into integral dA x I d 4x 1/2 dA squared minus JA. So there's the A field, is just a normal massless field. And this is then times the integral d eta. I've basically decoupled this totally. So I've decoupled it. This is the Lagrangian that I started with without any approximation. The feature here that's the highlight of this little exercise is that minus sign there. And minus sign there tells me that this is a well-defined path integral right here, but it comes with the wrong factor of I. And that's the same thing that we saw over here with the heavy particle being a massive particle. And what we're going to basically do is you put a plus I epsilon here and minus I epsilon there because it had both the factors of I were wrong. So you basically get a this field here that this is the time reverse path integral. Okay. The time reversal is anti-unitary. If I do time reversal on a normal path integral, I get the path integral with minus sign in front. That's the only place that I enters physics when you do path integrals. And so you get the same theory, but with a time reverse. This is going to cause troubles, of course. This particle here will propagate positive energies forward in time. This one will propagate positive energies negative time. This will give troubles with causality. And this is going to be a general feature. There's basically different causal directions. If you put this in, if you put this into real regular theories, you can make calculations that show there is causality violation. It was done by Lee and Wick. And Coleman had some contribution here. And then there's more recent work by O'Connell, Princeton, and Wise, which is much more readable to the modern reader. But you do get causality violations at short scales. However, you can integrate out this field. I can integrate this out. I just basically get J squared at low energies. We know that's not an unstable integral. And so it's causal at low energies. No, it's emergent causality in some sense. There's no causality has a causality at high energies. The low energy theory is causal. I will argue that that's a general property of many of these higher derivative theories, and that's the biggest and most important flaw to keep in track of. That's right. So it'll be
I think that if you have like just non-interacting A and eta,
Yeah.
it's easy.
Yeah.
So I take an I epsilon,
Right.
epsilon.
Right.
But if you have interaction between A and eta,
Yeah.
do that.
Yeah. Well, that's what you have to do in a particular theory, and yes, you can do that. But let me not talk about that now because I'm going to run out of time. Let's put that in discussion, okay? I'm going to have to shuttle many things to discussion. I'm going to also shuttle to discussion stability and unitarity of these theories because I'm not going to otherwise have any chance of getting close. Okay. So that's one feature of the high energy theories that I wanted to highlight is that we will almost always have this causality violation. The second thing I'd like to highlight is actually a prelude to Roberto's talk. And I'm going to do shorter than I had wanted to do here. But what I'm these theories have an intrinsic mass scale in them. That mass scale actually screws up the calculation of running couplings using normal methods. If I had time, I would give a longer description of this, but let me just basically jump to the conclusion is that when we get the matrix elements at one loop here, we're going to get things like some g squared 1 plus a log lambda squared. Let's do a cutoff over the mass squared calculation that appears in the theory. And then at high energies, there'll be terms that look like lambda squared over the energy squared. Okay, so I've neglected the mass compared to the energy in this one here. But this one, there are various diagrams that they typically are tadpole diagrams that look like this. In these higher derivative theories, that integral goes like d or p 1 over, well, it'll be p squared minus p to the fourth over m squared, typically. This will give a log divergence, and it will be a log lambda squared over m squared, as far as. Okay. So you get these type of log lambda squared over m squared out of the tadpole diagrams, but they have nothing to do with the running with respect to energy. Now, if you take your usual d by lambda d by v lambda of delta g, then you're going to get both these terms appearing. So this would go like a plus b. But if you're only interested in how it depends on energy, I'm skipping a step here. It's going to be a renormalization point, d by d renormalization point, g of mu r will just be b. So that you get different results if you take the usual calculations of running with respect to the cutoffs, or in dimensional regularization in respect to mu, or running with respect to the energy. This leads to differences, and the physical amplitudes only track the energy dependence. This mass dependence can be absorbed and does not change when you change the energy scale. Okay, so we get different renormalizations, and Roberto will show you that happens in quadratic gravity, and it happens generally in any of these theories where you have operators with different dimension in there. So implies that the usual calculations with respect to cutoffs is not physical. All right. So let me get back to gravity quickly. So if we get back to gravity, I'm going to do quadratic gravity. quadratic gravity is lambda r squared and c squared. This is a renormalizable theory. Which is in some ways a UV completion of the effective field theory. Roberto will tell you about the running. And he'll tell you that if you do the physical running, that this can be asymptotically free and tachyon free at the same time, which was not true previously. But the features that it has that it's going to, if these analogies with these simpler theories are true, is it's going to have indefinite causality at short scales. We may have to live with that. It's probably going to have this operator melting that I haven't said things, but I think it's going to be unitary. I will say that it's going to be unitary. And I'll hope that it's going to be stable. We can discuss these more. But the other feature that it's going to have is it's going to have this strong high energy behavior. Even with the operator melting, these terms here give you power laws in the energy. So it's going to have strong high energy behavior. Um, the strong high energy behavior was what we found in this theory here, where at high energies, these higher powers dropped out, but it's still the amplitude still went like energy to the fourth. And that's basically the best case scenario that you're going to get out of the quadratic gravity. And basically, I'm going to shorten my discussion of asymptotic safety by saying that it's more of the same. We have asymptotic safety generates all terms in the effective action. It's not clear that there will be operator melting. But you will certainly, at best, you're going to have a theory that has the high energy behavior of the quadratic gravity. There's not a guarantee of anything else. All right, so I did want to. Well, so it's one of the issues is that we've been focusing on the coupling constants. The coupling constants can be made to either go to asymptotic freedom or to a constant. That's what we've been focusing on, but I think that's not the right issue. The right issue is the amplitude itself is growing tremendously fast, and power growth of the amplitude overwhelms any coupling constant logarithmic running. Okay. Well, so we have to come up with some solution if if this is going to be a theory. I've postponed to the end here the part that I understand the least. Bob Holdham has suggested a solution to this. And it's rooted in a calculation that's from this model over here. He's doing the explicit calculation in those models. He points out that if you sum, so this was the scattering amplitudes just of the massless states. If you sum over the massless and the ghost, you get enormous cancellations. These are much stronger than you would even expect. So, and Diego's verified that in our calculation, if you sum over the massless and the ghost, you're going to have amplitudes that get very small at high energies. It's these extra minus signs floating around. I've been a skeptic of that for a long time, basically because arguing that you can isolate the massless state because the ghost is stable, the massive state decays. I mean, the massless state is stable, the ghost decays. I do a long distance experiment, I only get massless states. But I'm coming around to it. And so this is a point which I don't completely understand, but maybe it's correct. When the interactions are strong, you don't just do individual isolated states. And so let me imagine doing this scattering experiment where I'm coming along with these two particles. They're interacting very strongly. So in particular, they'll radiate particles very strongly. So these guys have initial state radiation and then they scatter. So this could be m equals to 0, but this is both. So if you start getting in this strongly interacting region, you get intermediate states that are always both particles. You're at very high energies. And then this guy gets very small. This one is also both. And you can do final state radiation at the end too. So if you're really in a place where you're no longer dealing with just elastic scattering like we did here, but have these intermediate states, the amplitude, there are a lot of cancellations going on. And this theory may, in fact, solve the high energy problem. I don't want to say that I endorse this yet, but nevertheless, this may be the solution to the high energy behavior of these theories. And given where I am on time, I'm just going to summarize. Okay, so the main points I wanted to bring up are some of the ones that are discussed less in the published literature. I do want to say that this is a quantum field theory, and the understanding of this quantum field theory is still evolving, and there's many things that I don't understand. But the one issue that you're going to have in all these high derivative metric series is causality. Causality may not be there. The usual definitions of causality may not be there at high energies, but still could be there at low energies. So emergent causality. There's issues about running couplings. That Roberto, Diego, and I are arguing that people have been calculating running couplings in these theories incorrectly. There's this idea of the operator melting. Which may help understand the high energy behavior. And then there's this high energy growth of amplitudes, which is an unsolved problem of which perhaps Oldham has come up with the solution here. but overall, the question that I'd like to answer, have as a discussion question is, what is success for this? How do we know we've got an acceptable theory? If it has some of these properties, we predict the coupling constants. How do we know we've had a successful theory? And that's where I'd like to leave it for the discussion period.
Okay, so we have 6 minutes for questions. There any question in person or line, Benjamin?
I want to ask about the asymptotic safety bit.
Yes.
If you go back to the original definition of Weinberg, what asymptotic safety
Yes.
means, it is formulated in terms of amplitude.
Yes,
and
it is.
amplitudes are constant at high energy. So
Right.
a bit confused. Could you maybe elaborate?
Yeah. That that definition is seems to me to be overly simplistic in it, because he's not allowing for the various couplings that carry dimensionality. So basically, he's thinking of many of these couplings as we think of them in usual renormalizable field theories. If you put extra, so the original Weinberg definition is basically dimensional analysis. He imagines that the amplitudes depend on the energies and on parameters like coupling constants, and rescales them by a renormalization scale, and then makes the argument that if these couplings run to constants or zero at high energies, that you can get a well-behaved theory. But if you have these extra dimensional parameters like masses, which are there, there's also m over e. And so there are extra e over m effects that are not in this dimensional analysis. And in some sense, if that argument was enough, this simple theory that we had here, where it went asymptotically free, the scale invariant theory, would have had a good high energy behavior. It doesn't, and the flaw in the dimensional analysis is these extra factors of mass that he didn't account for.
Thomas.
Very nice question. If I ever already see
Yes,
and it's not causal at high energy,
yes.
is it so obvious that it doesn't also then conflict unitarity? Because some physical processes could go back
Yeah.
in time and
Yeah.
sort of add information.
Yeah, so the argument there, which I did skip over somewhat, is if you do Veltman's proof and you just follow it through, it says that it's still unitary, and so we've done that. Okay, and if you do real explicit examples, I mean, in some sense, we did this and I didn't believe it, and so I started doing examples. You can see how it works, and it actually comes from the fact that you've changed the minus I in the numerator and the minus I in the denominator. The imaginary parts of that are the same. That's a very short answer to a complicated question.
Jan.
So, for back to Weinberg, yeah, say that any fixed point would serve as a candidate for quantum theory. I mean, we don't talk about it's unitary or anything, but you can define scaling at that fixed point and how you can turn around that fixed point. So I guess you're not saying that something is wrong with that argument. So that's a complicated answer in a relativistic field theory. It's much clearer in the condensed matter systems. Let's take a Euclidean quantum theory. Yeah. Because that's the easiest way to think about it. I mean, not talking about gravity, but talking about. Yeah, let's do scalar field theory. So any fixed point there, according to you. It's, so I'd say it's still a good theory. But the scaling that you get when you're doing, let's say, the functional renormalization group doesn't match the same as the scaling of the amplitudes in the theory because of these extra dimensional parameters. And so if you use the scaling that you get from the functional renormalization group, you're going to get extra large logarithms in perturbation theory. All right, let's hold this to the discussion after. Roberto's going to say something about this too. So let's hold this to the discussion. We have so many discussion periods.
Yes. Short question, Vice Raman. 1 minute.
The operator, field operator A.
Yes, yes. Yeah, they commute. They're at this stage independent fields. They're basically by the field when you put this into the path integral, it's an independent field, and then I've reduced it to this, which are independent fields. They couple to the same sources, but the fields themselves are independent. Okay. So they would
Okay.
commute.
So thanks, John.